Physics is all around us, influencing how we perceive sound and light, even when we are unaware of it. One of the most fascinating and practical concepts in physics is the Doppler effect, which describes how waves, whether sound, light, or water, change their frequency based on the motion of the source and the observer. To bring this concept to life, we use a simple but insightful simulation involving a duck in a stream and a kid in a boat a few kilometers away. This visual representation helps us understand how motion affects wave patterns and, in turn, our perception of frequency. Imagine a duck gently floating on a calm stream, kicking its legs rhythmically. Each time the duck kicks, it creates small waves that ripple outward in all directions. The duck kicks twice per second, meaning the waves form at a regular interval and spread out as concentric circles. If the duck remains still, the waves continue their predictable expansion, reaching the kid in the boat at regular intervals. The child, observing from afar, notices that the waves hit the boat at a steady rate. This is a representation of what happens when a wave source is at rest relative to an observer. Now, suppose the duck begins to move in the water. As it swims forward, something interesting happens to the waves. The circular waves that once spread evenly now become compressed at the front, the direction of movement, and stretched at the back, the opposite direction. This means that an observer in front of the moving duck would perceive the waves arriving at a higher frequency than before, while someone behind the duck would experience waves at a lower frequency. This is the fundamental principle of the Doppler effect. When a wave source moves toward an observer, the waves appear bunched together, increasing their perceived frequency, and when the source moves away, the waves spread out, decreasing their perceived frequency. The kid in the boat, observing from a distance, notices this change. If the child remains still while the duck moves towards them, they experience waves that arrive more frequently. But if the child starts moving away from the duck, they will perceive the waves at an even lower frequency than before. This is because the relative motion between the wave source and the observer affects how frequently the waves reach them. If the child were to paddle towards the duck, they would perceive an even greater increase in wave frequency because they are effectively shortening the distance between themselves and the incoming waves. The simulation becomes even more interesting when the duck increases its speed. If the duck moves at a speed equal to that of the waves it is producing, the waves in front of the duck start to overlap. This creates a buildup of waves at the leading edge, forming a noticeable front of compressed energy. This phenomenon is seen in the real world with sound waves when objects move at the speed of sound, such as when an aircraft reaches Mach 1. At this point, a sonic boom is heard on the ground because the sound waves overlap and create a sudden burst of pressure. Similarly, in our simulation, the waves in front of the duck create a high-pressure zone before the duck breaks through. If the duck moves faster than the speed of the waves, it surpasses the ripples it has created, and a shock front forms. This results in a distinctive V-shaped pattern behind the duck, often seen in real-life scenarios when boats travel quickly through water. The waves behind the duck form a trail, demonstrating how waves behave when an object moves faster than the medium carrying the waves. In aviation, supersonic jets create this effect in the form of a sonic boom, which is essentially a shock wave moving through the air. This simulation also helps us understand how the Doppler effect applies to sound. In everyday life, we experience this effect when an ambulance siren changes pitch as it approaches and then moves away from us. As the ambulance moves toward a stationary observer, the sound waves are compressed, making the siren sound higher in pitch. Once it moves past and away, the sound waves stretch out, lowering the pitch. The same principle applies to the duck's waves in our simulation, with frequency changes depending on the motion of both the source, the duck, and the observer, the child in the boat. The Doppler effect also has profound applications beyond water waves and sound. In astronomy, scientists use this principle to determine the movement of celestial objects. When a star or galaxy moves away from Earth, its light waves stretch, shifting towards the red end of the spectrum in what is known as redshift. Conversely, when a star moves towards us, its light compresses, shifting towards the blue end of the spectrum, blue shift. This is one of the ways astronomers study the expansion of the universe and detect exoplanets orbiting distant stars. Beyond astronomy, the Doppler effect is also crucial in medical imaging. Doppler ultrasound technology helps doctors examine blood flow in the body by detecting changes in frequency as blood moves through vessels. This allows for the diagnosis of conditions like blocked arteries or heart valve problems. Similarly, law enforcement radar systems use this principle to determine vehicle speeds, measuring how radio waves reflect off moving cars. For students, understanding the Doppler effect through the simulation provides an intuitive grasp of how motion affects waves. By visualizing the duck's movement and the resulting wave patterns, they can relate this concept to real-world phenomena like sound changes, weather radar, and space exploration. The simulation also encourages critical thinking, as students can experiment with different speeds and observer positions to see how wave patterns change. One of the biggest benefits of such a simulation is that it breaks down complex physics principles into simple, relatable scenarios. Rather than memorizing abstract concepts, students can see and predict how waves behave under different conditions. This hands-on approach makes physics more engaging and less intimidating, fostering curiosity and a deeper appreciation for the subject. Ultimately, the Doppler effect is an essential principle that extends across multiple scientific fields. Through this simulation, students not only gain a clear understanding of wave behavior, but also see its significance in everyday life and advanced technology. Whether studying the movement of ducks in a stream, listening to passing sirens, or analyzing distant galaxies, the Doppler effect serves as a powerful tool for interpreting the world around us. By making these concepts more interactive and relatable, physics becomes more than just equations. It becomes an exciting journey of discovery.